Vanakkam. Welcome to this course on biomedical instrumentation. In the previous set of videos, we looked at electroencephalography or EEG or brain electrical activation. The previous week, we looked at ECG. In this set of videos starting from now, we will look at what is called as electromyography. Myo means muscle. Myo means muscle. MYO, myo means muscle. Electromyography means electrical activity of muscles. So, in this video, we will introduce the notion and the concept of electromyography, and we will look at the EMG block diagram. Going forward, I will simply say EMG. When I say EMG, I am referring to electromyography. So, we will look at EMG block diagram in this video. What do these do? EMG, essentially when I say myography means muscle activity, essentially in this case we are interested in skeletal muscles. What are the skeletal muscles? Skeletal muscles are those that connect one bone to another bone via tendons. The details of how muscles work is beyond the scope of this course. I teach a full course on neuroscience of human movements. Neuroscience of human movements. Parallelly offered with this course in this semester in 2025 in NPTEL, in which I discuss the details of how this works, how the muscles function, and the physiology of EMG generation I discuss in detail. We will keep our discussion of physiology to the minimum in this course, because this course is a course on biomedical instrumentation. Okay. But still we need to know minimal physiology to understand how this works. So, essentially this is the recording of electrical activity of skeletal muscles. So, what is happening is we will discuss the details as we go along, but there are other muscles that whose activity we recorded previously. For example, there is a single muscle that has its own type, that is the cardiac muscle, whose activity we discussed, we measured in the previous week, that is the ECG, electrocardiography. This electromyography or electromyogram in this case, this signal, EMG signal, is generated due to flow of ions across muscle membranes during nerve stimulation, during neuronal stimulation. Essentially can give us an idea about the health or the absence of health of muscles and motor neurons. Actually, what is happening is there are motor units and action potential trains of motor units that happens. There are motor neurons. These motor neurons, the so called alpha motor neurons, and then there are the gamma motor neurons. The details are there in my other course, but here primarily we are interested in the alpha motor neurons, whose cell bodies are located in the spinal cord. They send their long axons to muscles. Note that muscles are also excitable cells, and axon collaterals of these motor neurons innervate specific fibers in the muscles. The relationship between a motor neuron and the muscle is such that every time the alpha motor neuron sends a command, the muscle must obey. And it turns out that several motor neurons connect to a given muscle, but a given fiber is innervated by only one and exactly one motor neuron. That is, one fiber is innervated by a given motor neuron, but one motor neuron can innervate many fibers, one to many. Like I am now teaching, hundreds of you are listening. This is a relationship. I am the alpha motor neuron, all of you are muscle fibers. If you are taking only this course and no other course, for a given student there is one and exactly one teacher, like that. So, from the viewpoint of the muscle fiber, there is exactly one alpha motor neuron from which it receives innervation, but one alpha motor neuron can innervate multiple muscle fibers. The details of this is beyond the scope of this course. For now, it is sufficient to say that the number of motor muscle fibers that are innervated by a given motor neuron essentially is the so called innervation number. A motor neuron and the set of all muscle fibers that it innervates is called as a motor unit, and the action potential that is happening in the motor unit is what you are measuring using the electromyogram. So, electrodes captures this activity as graphs or sounds or values. Imagine you are having a microphone on the surface of the skin that you can hear. When the muscle is active you are able to hear. Actually that movements are not audible. In the good old days actually EMG signal was outputted to speakers, Even now that is there. That topic is called as sonification of muscle activity, sonification. In the good old days, so every time when a given muscle is contracting, you will hear beeps and activation. At other times, you will feel silence in the speakers. That used to be the case. So imagine I am keeping a microphone on the muscle, and you are hearing the muscle activity as the sound in your this. That's essentially what EMG is doing. So EMG measures activity during rest. During rest also there will be some baseline activity. It says no signal. That is not true. Actually what you have is a baseline activity. There is always some activity, baseline. When there is no signal in the muscles, essentially that means that you are dead or you are in deep sleep. Usually there is some signal, some baseline activity is there, and mild and forceful contraction, that is also something that you can compare with. Here is an example of an EMG system. It is a muscle Whistler system, it seems, the name of the system, muscle Whistler system, that measures activity from, say, I think only 1 or 2 channels, I think, then you can measure. Like this there are multi-channel EMG that is quite often used. Here is a block diagram of the EMG. You have a pre-amplifier that collects information or data that first performs the first amplification of the signal, and then you have the power amplifier that or the next stage of the amplifier, which you then pass on to the analog to digital converter. What is the resolution? Minimum 16-bit. Okay, and then you perform digital signal processing using a computer. You display this in the this. Now, what is the typical amplification required? For EEG, we said minimum amplification required is 10,000. For EMG, minimum amplification required is about 1,000. Total amplification. For both stages included, the total amplification required is about 1,000. For EEG, it's about minimum about 10,000. The sampling frequencies that you are looking at, about 2000 hertz is enough. Sometimes people sample about 20,000 hertz. There is no practical use of that. It only means you will have to process a lot of samples. It just wastes resources. So above the Nyquist cutoff frequency, if you are, there is only so much value in collecting, in oversampling. There is only so much value in that. So this block diagram essentially shows the DAQ system and signal processing of an EMG system. The preamp and the differential amplifiers together essentially have a pass band between 10 hertz to 1000 hertz. The signals usually are between 20 hertz and 1000 hertz, or 10 hertz and 1000, depending on the book this varies. These signals are usually sampled at about 2 kilohertz to 5 kilohertz with 16-bit resolution, 16-bit ADC, and then these are rectified and then smoothed with a moving average filter or the running time window average with a window size of, some windows is depending on the situation, sometimes 240 milliseconds, that is updated every 80 milliseconds, depends on the window size, depends on the application. This window size and the update time may vary. These process signals are usually normalized. It turns out that for the same person, between sessions the amplitudes might vary. So EMG may not be comparable even within the same person for the same muscle, which is why it is important, it is critical to normalize this using what are called as maximum voluntary contractions, and then you normalize it with respect to that session's MVC, maximum voluntary contraction, or MVC, technical term. Yes. These waveforms are then stored, first first rectified, then integrated or smoothened. This waveform can also be printed, but usually that is not done. Unlike EEG and ECG, it is quite unusual for someone to print EMG. Okay. Yes. They may contain frequency components extending up to 10 kilohertz, but that is quite unusual. Usual frequencies are below are around 1 kilohertz. So, such high frequency signals 10 kilohertz cannot be used and recorded using conventional pen recorders. The regular EEG, ECG type pen recorders cannot actually print 10 kilohertz signals. So, usually these are displayed on a CRT screen, or nowadays on a LED, LCD screen, LCD or LED screens, CRT, old technique. So, modern EMG machines are almost always computer based, and they are available both as a console or as a or in both on desktop and in the laptop modes. Right. So, because they require this advanced signal processing. So, with this we come to the end of this video. In this video we introduced what is EMG, and we discussed the block diagram of the EMG. If you are interested in understanding how the EMG signal is generated, motor units, motor unit action potentials, how the neuromuscular junction functions, and this, I request you to take my other course on neuroscience of human movements. With this we come to the end of this video. Thank you very much for your attention.